Welcome to The Explainer. Today we're talking about the invisible locks that protect, well, pretty much everything in our digital lives. They are everywhere, totally unseen. But they're about to face a brand new kind of key, a quantum key, that could literally change everything.
So let me ask you a question. Is your online life truly private? It seems simple, right? But the answer is, incredibly complicated. Every single day you put a huge amount of trust in a system you probably never even think about. But how strong is that trust really?
Think about it. You type your credit card number into a website, you hit buy, and you just trust. You trust that a week later you're not going to see a bunch of fraudulent charges. That trust is all because of something called encryption. But what happens if the very foundation of that encryption is about to get completely rocked? Okay, let's get into it.
So to really get a grip on this new threat, we first have to understand how we keep secrets safe right now. And the system we use, it's actually brilliantly clever. It's all based on something called public key cryptography.
Now I know what you're thinking. This sounds totally backwards, right? If the key is public and everyone knows how to lock the message, shouldn't everyone also know how to unlock it? Well, no, and that's the genius of it. The whole method is built to be easy to do one way, but incredibly hard to undo.
The absolute best way to picture this is with a treasure chest. Imagine a website sends you an open, empty chest. You take your sensitive info, your credit card number, and you put it inside. Then you just snap it shut, and the second it closes, it locks itself automatically. Now, the only person in the entire world who can open that chest is the one who sent it, because they hold the one, single, unique key. Your information is perfectly safe on its journey.
In the real world, that treasure chest lock is actually a math problem. The most famous example uses prime numbers. See, it's super easy to take two massive prime numbers and just multiply them together. But if all you have is that final gigantic number, trying to work backwards to find the two original primes that made it, it's practically impossible for a normal computer. The public key lets you lock the box, but you need those secret prime numbers to ever get it open again.
For decades, this system has been the bedrock of digital security, a lock so tough that it could take the world's most powerful supercomputers hundreds of thousands of years to pick. But what happens when a new kind of computer shows up? One that just doesn't play by the same rules at all.
And this is where the sheer scale of the threat just hits you. A task that is, for all practical purposes, impossible for our current tech, something that would take 100,000 years, could be solved by a powerful quantum computer in a matter of minutes. Just like that. The digital locks we rely on for everything would basically just melt away.
And we're not just talking about your Amazon account here. This is a fundamental risk to global banking, to private communications, even to national security. So what's the takeaway? We need a new kind of lock. And the good news is, researchers are already building them.
Okay, so how do we fight back? Well, the first approach to solving this quantum problem, funnily enough, doesn't actually involve any quantum physics. It's all about outsmarting the quantum computer with better classical tools.
It's called post-quantum cryptography. And yeah, the name's a little confusing. It doesn't use quantum mechanics. It gets its name because it's designed to be secure after quantum computers become a reality. It simply uses different kinds of math problems that, as far as we know, quantum computers aren't any better at solving than regular computers.
So, going back to our analogy, post-quantum cryptography is basically like throwing out that old prime number treasure chest and building a brand new one from scratch. One with a completely different, much more complicated lock that even a quantum locksmith can't pick.
But there's another path, a much more futuristic one. Instead of just trying to build a lock that quantum computers can't pick, what if we used the weird, wonderful rules of quantum mechanics itself to create a perfect, absolutely unbreakable key?
This is called quantum key distribution, or QKD for short. And in the world of cryptography, whenever we need to explain something, we always talk about two people trying to communicate securely, Alice and Bob. And here, they're going to use the fundamental laws of physics to protect their conversation. Okay, so here's the simplified version. Alice sends single particles of light, photons, over to Bob. For each photon, she randomly sets a property, like its spin. Bob, on his end, also randomly chooses how he's going to measure that property. Afterwards, they get on a normal phone line, totally public, and they only compare the settings they used, not the results. And whenever their settings happen to match, they keep that result. All those matching results, strung together, become a new, perfectly secret key.
Now this is where it gets truly brilliant. What if a third person, we'll call her Eve, the eavesdropper, tries to intercept those particles while they're in mid-flight to try and figure out the key? Well, she has the exact same problem Bob did. She has no idea which setting to use for her measurement.
And this brings us to one of the wildest rules in physics, the no-cloning theorem. It basically says you cannot measure a quantum state without changing it. The very act of Eve looking at a particle alters it. So later when Alice and Bob compare a small sample of their final key to check for errors, they will immediately know something is wrong. The eavesdropper's presence is instantly revealed. The laws of physics itself become your burglar alarm.
So there you have it. We've got two really powerful new paths to protect our data in a quantum future. Let's just quickly see how they stack up against each other.
All right, let's break it down one last time. First, you have post-quantum cryptography. That's classical, non-quantum code that quantum computers just can't break. This is actually in development and starting to be adopted right now. Then there's quantum key distribution, or QKD. That uses quantum weirdness just to share a key securely, which you then use with normal encryption. The technology exists today, but it's not very common yet. And finally, there's the idea of using quantum effects to send the entire message. That's still pretty much just theoretical for now.
You know, we are living through a massive shift in what it even means to keep a secret. The race is officially on. On one side, you have the code breakers with these incredible new quantum machines. And on the other, you have the code makers, building the next generation of digital locks. The real question isn't if this change is coming, but how are we going to adapt when it finally arrives?